This is the final lecture of virtual memory management. Very next lecture is supposed to be file systems, and that's why I would love to throw together a lecture on hypervisors. I could either do that, or we could skip class on Friday. I haven't decided which we're going to do yet. But since the next week is only 2 lectures, we will need to start discussing file systems pretty quick so that you're ready for Project 6. But anyway, that's basically where we're at right now. But today we were going to sort of wrap up the discussion of page management by talking about page allocation. So this is the question of how do I decide how many pages each process should actually get to work with in its pool of, I should say how many frames it gets to keep in physical memory. So yeah, page replacement policies we talked about. These are for when you have to evict a page to free up a frame. Now, basically, if you think about it, we have physical memory, and it's just like we talked about last time. Last time we had 64 megabytes, or that's how Pintos limits things. You can have up to 64 megabytes of frames, and then you have to decide how to allocate these frames. Pintos cuts it in half and says half is for the kernel, half is for user processes. No real application or real OS does that because it would just be way too many pages for the kernel and way too few for user processes. But anyway, we do have some limitations that we have to work within, and anything left over can be allocated to processes, but we want to do this intelligently. Now, there's a couple of things that the OS can control. Like if you think about what the OS can do as far as scheduling and managing resources. So we can figure out how many frames are allocated to each process. Okay, so that's one thing we could control. We don't do that in Pintos, but we could. And the other thing is the degree of multiprogramming, or how many processes are actually running. Now, this whole notion of the degree of multiprogramming, we talked about this before, like how many processes do I actually try to run at once? That is, how many can be ready or running. Remember that the medium-term scheduler can influence this if an OS has a medium-term scheduler. I don't think any of us have actually used OSs that have a medium-term scheduler because it's not really as common these days. But that would be how you control the degree of multiprogramming. Okay, so page allocation process or policy is how we figure out how many frames each process should actually have. Okay. Now, the way that they figure this out is they want to try to satisfy the needs of every process, as far as how many pages it wants to utilize and so forth. And if we lived in a perfect world, every process would have all the frames that it needs. So we'd never generate faults except when we access something for the first time. I mean, that would be beautiful if you had a ton of memory, a ton of physical memory. As you ran, you would only incur faults when you actually accessed a new page for the first time. But the reality is not so nice, especially because we'd like to do as much as we can with as little as we can. So basically, we try to keep the page fault rate limited to something that is tolerable. Okay? And the interesting detail of this, like I say here, when a process page faults, it slows down that specific process. Obviously, the OS does some work as well, and work we do page fault handling. It's not work that is solving user problems. But the nice thing is that when we have multitasking, even if you had CPU-intensive processes, so they have large CPU bursts, basically no I/O bursts, well, as long as they keep faulting, then they'll have some I/O in there, and so we'll be able to context switch to another process and let it run for a while. So you can see that a page fault mechanism is some sort of tolerable page fault rate actually allows our system to stay more fully utilized over time. Okay? So that's kind of the interesting thing about this. It allows other processes to get access to the CPU, and it allows us to leverage the I/O subsystem. And the last thing is that it sort of allows us to, again, overcommit on virtual memory, even when we don't have enough physical memory to satisfy it. So yeah, question?
Can you talk about how, the work that we're doing to handle the page fault is some work that their user processes aren't getting to do?
Yeah.
What about, is there not also an overhead? Because when you're doing the paging I/O, right, you're taking up the disk drive.
Yeah.
And so if another page, other processes can then block because you're taking up the bus for doing I/O.
Yeah, so it's true. I mean, if you had some I/O intensive operations you were doing, then this paging would be a lot less appealing. So the nice thing is that usually that's I'm trying to think. I honestly I think that I don't have enough information to be able to speak too intelligently to that. So I probably won't. But your point is absolutely valid. If you have I/O heavy operations that you're doing, then page faults will interfere with that. No question about it. See, what I was going to say is that OSs and disk controllers can schedule the I/Os in an intelligent way, so that that'll be as low cost as possible. But you can still push the system until it becomes, a significant overhead. The other thing that I was going to say about that, is that the whole scheduling of I/O aspect of things is what causes some of the consistency issues in databases and other systems, because you may get reads and writes performed in orders other than the order you issued them. So you can run into that as well. But it's funny because I've been doing programming and computer science for several decades now, and I think the only bottleneck that I've ever run into that was really serious and severe was with the CPU. Like I/O bottlenecks, I've never encountered as being a severe limiting issue in a system. That doesn't mean it can't happen, but that's why I don't know anything about specifics about this, because I've never actually encountered that kind of a scenario. But it's totally feasible that could happen. One interesting issue that you will run into, actually, leading into this, though, is that the I/O can actually become a bottleneck if you're paging so much. And so this is not paging interfering with other I/Os, but this would be paging interfering with paging, where basically you have the I/O subsystem's demand exceeding its capability. And so that's where we run into this issue of thrashing again. And we've talked about this term before. We've talked about it in the context of conflict misses of user programs on hardware caches, so we're talking processor caches. Paging is another great example of where this can occur, where the page fault rate is so high that the I/O system is completely overwhelmed and the CPU is idle. It's basically sitting idle because it's waiting for I/Os to complete. So that sucks. Comes from when tapes were used for external storage, and I can't even imagine what that would have been like to be in a data center listening to tape drives whirring, because those were the reel-to-reels back in that time that would have been used as storage, swap space. Okay, now what's interesting about it is how the characteristics of thrashing can be manifested. So depending on how page allocation works, we can either have one process thrash, or we can have all processes thrash. Okay? And that sort of gets down to the question of how do we actually assign frames to pages. Okay? So thrashing happens when the total number of frames exceeds the number of frames available in the system. So basically what we're saying is every process would prefer to have a certain number of frames that it's using, and if that number exceeds the number available in the system, then we can start seeing this issue manifest. Okay? And so the issue is that you have a process generates a fault, through no fault of its own, shall we say, because it's accessing something that the OS has said, yes, this memory region is valid for you, causes a fault, the OS kernel has to resolve it somehow, and it steals a frame from somebody else that's using it. So then we get another fault. We're going to cause another fault again very quickly. Okay? So we'll talk a little bit about this problem as we go through this. Basically, you can imagine a lot of scenarios in which this would occur. Okay? So we have, for example, 4 processes running. Each one has a virtual address space of 10 pages. So that's the full address space, but then the part of it that it's actually using, we call it the working set. I don't introduce this term until later in the lecture, but we call it the working set. It's the number of pages that I'm actually working with at a given time. Okay? So we have 20 frames. We have 20 pages that are in processes working sets. No biggie. We're not going to be generating faults. But if processes then increase their working set sizes dramatically, unexpectedly, then we start having problems. The requirement is for 30 frames, the system only has 20, and so now we're starting to generate faults regularly. And if the fault rate exceeds the I/O system's ability to handle it, then we're going to start seeing thrashing. Okay. Now I say this is the part that's interesting, and this is something we're going to be exploring a little bit more. I say here that this scenario can cause all processes' page fault rates to increase. Okay. That's really the question. When a process faults, do you take a frame that it is using for another page from that process, or do you take it from a different process? That's the question that really can affect who suffers when thrashing starts to occur. Because if you look at this, you have 4 processes. 2 of them, we say, are accessing 5 frames. Okay, so, and then 2 of them suddenly increase their working set size to be 10 virtual pages, so they need 10 frames. Well, what if we just keep taking them from the processes that demand 10 frames? So then they would be the ones that are thrashing. That would prevent the other processes' page fault rates from increasing. Okay. Depending on how we manage whose frames are able to be taken away. That's really the kind of the question here. Okay. So yeah, this is what I was talking about before. Processes have working sets. And the degree of multiprogramming is basically how many processes are we trying to run at a given time. And so qualitatively, the textbook has this picture. There's no paper cited, so I couldn't point you to quantitative measures. I'm hoping that the graph is backed by quantitative measures. But this is the idea. You increase the degree of multiprogramming, CPU utilization increases, because processes will do CPU bursts and then I/O bursts, and while they're doing I/O bursts, they're not using the CPU. So as we increase the degree of multiprogramming, we should see CPU utilization go up. And then at some point, each process has a working set of pages it would like to work with, so that increases the requirement on frames. At some point, paging starts to increase. And then at some point, paging increases to the point that the I/O subsystem can't keep up with the page fault rate. And that would cause the CPU utilization to crash again. Okay. So again, this is the observed behavior of systems in a qualitative sense. Okay. And so you say that the system is starting to thrash. Okay. Now, if you can control the degree of multiprogramming, then you could start saying, well, you know what? I've overcommitted process physical memory to the point that I can't satisfy all the processes without the I/O system being completely saturated. And so this is where a medium-term scheduler would be able to suspend processes. Okay, so this is the idea. Long-term scheduling, you could basically prevent when processes are added to the runtime, so that they basically, the OS prevents saturation from occurring. Or medium-term scheduling, you would go ahead and start suspending processes, and then you could resume them when other processes terminate. Like if you suddenly discovered that one process needed a lot of frames, then you could either suspend it and allow other processes to finish, or you could suspend other ones and let that one finish and get out of the way. So you could do something like that. Okay, so you can do this kind of stuff. Look at the page fault rate. We're actually going to be talking about that in a little bit, but you can always, there's a couple of measures you can look at to decide what to do in these situations. We're going to develop that a little bit more by the end of the lecture. Okay, let's see. Yeah, now this is what we normally do. Like everybody who's got a computer generally relies on the user to control the degree of multiprogramming. So there's only a short-term scheduler. There's no medium or long-term scheduler. So the OS just starts processes based on the user's requests. If the user decides to start a lot of things and use up all the frames, then that's no biggie. That's the user's problem. And then the user is the one responsible for evaluating the performance to see if it's an issue or not. Okay, so generally the user will just suspend or stop things based on system behavior. And honestly, computers are getting good enough that every time I ask students about this, fewer and fewer students have encountered issues of thrashing. I don't know if you guys have ever encountered thrashing on a computer system that you've used. When I was your ages and I had a computer with spinning magnetic disks, and we'd have swap space, and we would have amounts of memory measured maybe in gigabytes if we were really lucky, then sometimes you would be running programs and you would just see suddenly the computer was really slow at getting work done and the hard disk light was just on. And that's all it was. The hard disk light was just on, and that was because it was having so many faults. It was just moving data back and forth from swap to memory and vice versa. So that's thrashing. And I would encounter this relatively frequently. Like, you would definitely run into it from time to time. It's, in my experience, been exceedingly rare that I've encountered that more recently. And we have so much physical memory on our computers, and a lot of times we don't run processes that actually tax the system. So have you guys ever encountered this kind of thrashing behavior? Yeah. Have you?
Not really.
Yeah. I mean, I imagine that there's been a couple of students that have come through that really like doing computer players for various kinds of games, and I would imagine like a game search tree could be sufficient to really use up memory. But yeah, I just haven't seen programs that really stressed out the virtual memory subsystem in this way in quite a while. So it may just be we have so much physical memory. Okay. This is the crux of what we've been talking about, and so I'm a little bit annoyed with some of the earlier slides, just full disclosure, because there's a really fundamental question to think about when you design page allocation policies, which is, where do you take the frame when a process wants to load a new page? Okay, so you could either have a global replacement policy, or basically you can take a frame from any process that's running. Ideally, you make a good choice, you make a careful choice. That's the eviction policy's choice. But a global replacement policy means that you can take it from anyone. You're not constrained to take a frame from the process that just generated the fault. Okay? So, benefit of this, well, you get a huge amount of flexibility in figuring out what process gets frames, okay, and what process doesn't need it. If you have a process that only needs 4 frames for its virtual memory space, cool, it only has 4. If you have another process that needs 150 frames, no biggie. It just sort of gets those frames over time. And so that's the thing that you notice with these kinds of systems, is that the policy is really flexible in responding to what processes actually need as far as frame allocation. Okay, this is what Pintos is doing. Probably have already figured that out. Linux does this as well. So this is a pretty common approach, actually, to have a global replacement policy. This is where you run into the issue, though, that if you overcommit physical memory, and now every process needs more frames than it has, then you start getting this global thrashing behavior. And so this is where one process suddenly increasing its working set size can cause all the processes to thrash. So that's the part that's really sad. That's the issue with global replacement, is that you can start seeing thrashing for everyone. Now, another approach is to have a local replacement policy, where basically, if a process page faults, the OS tries to satisfy the new frame request from the process that caused the fault. Okay, so that's a local replacement policy. So process A caused the fault. Process A has to give up some other frame. Okay? And so basically, this allows the OS to really tightly constrain what processes get what frames or how many frames. Obviously, also, it's not as flexible in responding to changes in process virtual memory needs. Okay? So like I say here, the strength is now if a process starts behaving badly, now only that process suffers. Presuming, like you mentioned, that we don't have massive amounts of I/O being performed by other processes where thrashing would actually interfere with the I/O speed. But at least as far as CPU performance, other processes would be able to continue running because they'll still have all the data they need in memory. Okay? But the limitation, which I've already mentioned, is that the number of frames that you assign to each process can't vary as quickly so that you can allow processes to grow their working set sizes or shrink their working set sizes quickly. You can't really respond to that as quickly. So that's why I said before, most OSs, they'll use a global replacement policy because they just find that it works best with responding to processes' behavioral changes or memory requirement changes. Okay. Any questions about global versus local replacement policies? I mean, I think it's really straightforward. If you're talking local replacement, then you have an interesting question of basically how many frames do you set as a process's available set of frames off the bat. And so if we had some number of frames, we call this M, and some number of processes N, then we basically could have a simple policy where we divide the number of frames amongst all the processes, and that would be an equal allocation policy. Okay, so that would obviously be a simple one, but we know this isn't going to be very good because, I definitely have some programs that use a lot of memory and some programs that use very little memory. And so that's not going to really suit a typical kind of circumstance very well. Okay. So you could look at the virtual address space. This is a little bit more sophisticated. Basically, you look at the process and you look at what parts of its address space have been initialized or assigned. Okay. And again, you guys are familiar with this because when you have the ELF file, it says, here's my address space, here's the description of the address space for the static program. You can load that in, you can use it directly in the virtual memory system. Your malloc would say this is the size of my heap. You'll know the maximum size of your heap, and as your stack grows, you'll know the size of your stack. So you could figure out the address space size of each process as it's running, and you can figure out the sum of all of those things. Okay. And then you could implement a proportional allocation policy where you try to give processes numbers of frames that correspond more or less to their virtual address space sizes compared to the overall virtual address space allocation. Okay. So to me, this already looks better because now if we have a process that says, oh, I'm using a lot of space, well, then it gets more frames. And if you have a process that doesn't need much space, it doesn't need as many frames, so you give it fewer. Okay. And of course, if you're talking global replacement, there is one context in which global replacement could utilize a policy like this, and this is if you're trying to pre-page. You're trying to pre-fetch pages to avoid page faults and IOs later on. Like if you really wanted to, somebody's using a lot of heap, and so you want to go ahead and just stick some frames in there or something like that. Okay, that's about the one situation I can imagine where you'd like to use an allocation policy with global replacement. But these policies are going to be much more usable with a local replacement policy. Okay. Let's see. Yeah, the issue with both of these policies is as you increase the number of processes ready or running, then that'll obviously cause issues with all of the processes. So like I say here, equal allocation, well, n is on the bottom, that's the number of processes, so obviously as we increase n, the number of frames that each process gets is going to shrink. Same thing here. As we increase the number of processes, the overall virtual memory size, which is S, so that's the sum of the process virtual memory sizes of all processes, that'll increase. So again, we're going to be seeing fewer and fewer frames for each process. Okay. So you can see this is about allocation. This is not about eviction. This is more about allocation. That we're starting to take away frames from processes, and so that's going to increase the likelihood of thrashing. And so this is where, what this really illustrates is the importance of controlling how many running processes you have. Okay. I was actually thinking about this earlier. Like, we don't have systems with medium-term schedulers, but there's no reason that you couldn't have a system with medium-term schedulers, because many computers have background tasks that they have to perform for maintenance and so forth. And so it could make sense to have a clever scheduler that knew some tasks were batch tasks or background tasks that needed to be performed on some, limited scheduling requirements, and you could definitely use medium-term scheduling to manage those processes in the context of other processes. The problem is that you can always use priority to solve these problems as well. Like you can always say, well, they're just low priority, and other processes get to run, and then you don't need a local replacement policy. You can use a global replacement policy. Because if a process is not running because it's preempted a lot, it won't access its pages, and then those pages can be evicted. So, I don't know. There just doesn't seem to be a lot of room for medium-term schedulers in, current systems. That might be something interesting to look into. Okay, working set model. So, basically, I see your variations in process page frame requirements. We're sort of assuming that everybody's going to need a number of frames proportional to either the overall memory size divided by the number of processes running, or just by looking at the virtual address space. But we know that that doesn't really satisfy the real world situations that we encounter. The process behavior changes, memory requirements change, and so forth. So basically, we'd like to have a policy that uses the dynamic behavior of processes more intelligently. Okay. So here's an idea. We're going to try to quantify the working set size. You may notice that this is very similar to the idea behind WS clock. We talked about WS clock when we were talking about eviction policies. And so if we can somehow guesstimate what the process's working set size is, then we can use this to guide frame allocation decisions. Okay? So, WS clock, right? We look at the current time and go back a certain distance in time, which again we're calling tau. And if we can look at the number of pages accessed within this window, then we can use that as a guess to what is the working set size. And then we can use that to guide page frame allocation to processes. So basically, you'll notice a lot of similarities between this approach and WS clock and also aging. Basically, the mechanism is very similar. It's just that it's going to work at a much lower resolution than aging even would. Okay, so we have a b-bit value for each page. Maybe it's 4 bits, something like that. It's really tiny. It's not that large. And basically, we do the same thing that you would do for aging, except much lower resolution and much longer interval between ticks. Okay? So you shift the value right. You put that access bit into the topmost position on your b-bit value, and then you clear the access bit. And so basically, any page that has been accessed within that window, whatever b is, b times the timer tick size, you assume that that's in the working set. If it has a 0 value, you assume that it is now outside the working set. Okay? So that makes it pretty easy. And like I say here on the slide, this is supposed to be a really low resolution thing. Just basically saying, has this page been accessed any time in the previous n ticks where the time between ticks is relatively large. So you can see how you could build an aging policy and also build something that determines working set size into that aging policy. Because aging already would have to traverse all the frames and see which ones have been accessed. I should say pages and see which ones have been accessed. Correspondingly, you could also do this with any other policy that incorporates timer ticks. So like WS, well actually I shouldn't say WS clock. I think, yeah, WS clock does incorporate a timer tick. But anything that has a timer handler, you could use a mechanism like this to determine working set size. Okay, does that make sense? Just an idea. I guess it should be comforting that you don't have to think about this for Pintos, because while this is cool, and I'm sure you could easily figure out how to build it, figuring out what to do with it would be more complicated. Okay, so once you know process working sets, and of course, more accurately stated, estimated, then you can use that to set the degree of programming, degree of multiprogramming, which is kind of a neat thing because you have this guess as to how many frames each process needs, right? You've done this estimate, and you say, this process needs 9 frames, this process needs 14 frames, this process needs 3 frames. And so if you have all these processes and you have a guess as to their working set sizes, you can add that up and say, oh, this exceeds the number of available frames in my system. So I'm going to have thrashing. And you could say, well, I'm going to take these processes out, maybe the low priority ones you could suspend. Okay. So you can see that this is kind of an interesting thing that you could use this estimate of working set size to guide medium-term scheduling choices. Now, what do you do with the new I mean, obviously, this doesn't help with long-term scheduling. How do I know when to introduce new processes if I'm a batch system? Well, you kind of don't. You have to see the behavior of the process. So this kind of thing would work great for medium-term scheduling, but then long-term scheduling, you might be, you just have to guess. Or maybe use previous observed behavior, or use the ELF files virtual memory description, or something like that. Okay. So the other neat thing about this is if you have estimated what the process's working set size is, that means you also know what pages were being accessed. So if you know what pages were being accessed, then when you unblock or resume scheduling a process, you can go ahead and preload those pages back into memory. Okay? So this is great because now you can actually make it so that when you restart, you don't have to do demand paging. You can already preload those frames, those pages into frames, and then presumably you won't get a bunch of faults right off the bat. Did you have a question or comment? Okay. So that was one thing. I really like that approach. I think it's cool. But obviously there's a knob you have to decide on the setting of, and that's the size of your window. Like the window size can really dramatically affect the quality of that estimate. So here's another one. Go ahead and add this. I'll say this as well. Page fault frequency tends to be what most OSes use to determine if there's a problem. Okay? You can either look at how often a specific process is faulting, because again, the kernel knows everything. It can keep track of this. Or if you have a global replacement policy, then global allocation policy, you can use the overall page fault frequency to decide if you have a problem. Okay. So that's the another approach. It's sort of the other possible way that people have explored solving this problem. So you just say certain page fault frequency we're happy with, and again, it would be a really interesting question to figure out how do you determine what an acceptable page fault rate is. Because obviously that depends on the I/O subsystem. So I suppose you could, even if you were a really clever OS implementer, you could say the fault occurred here, this is how long it took to be resolved, so you could use that amount of time to figure out how long a page fault resolution takes, and then you could use that in combination with the current frequency of page faults to try to guess as to when you're in an unacceptable range. Okay. So one of the things that a lot of, again, this is one of those things that you notice, is if you have a solid-state drive, if you're using a solid-state drive for your swap, virtual memory is super fast. I mean, solid-state drives are great. They're so much faster than spinning hard disks as far as implementing virtual memory. And so, I've been on solid-state drives for most of my computers for years now. And if I restart an application or something, maybe I had it in the background, so I know all of its pages have been evicted. By that point, they're being used by other programs. And then I go back to it, I find that the startup time for that is really quite fast. I mean, maybe the longest it'll be is like a second. It used to be that it could be 20 seconds or something like that. And so solid-state drives really make things faster. And the point being that you can satisfy a much higher page fault frequency against a solid-state drive than you could against a magnetic disk. So if you can estimate that based on the amount of time it takes to resolve faults, then that would be a pretty clever approach. Okay, let's see. Yeah, so pager can aim to keep the page fault frequency, but within a desirable range. So again, like lower bound is not 0. That seems really weird. But page faults allow other processes to get to the CPU. So it's a nice kind of alternate tactic for when your scheduler isn't preempting enough to give everybody a time slice as often as they may want. So instead, we'll also allow them to fault, and that'll kick them off the processor sometimes. Okay. All right, so yeah, if the process, again, this is in the context of local allocation. If a particular process exceeds the upper bound of the page fault frequency, then the OS can just grant it more frames, and then it'll be a little bit better. If it's below the lower bound, okay, again, we're talking about fairness, I guess, and the OS says, some processes are faulting more frequently than others. Maybe we should take some frames away from the ones that have too few faults, okay, so that everybody suffers about the same. Okay. Okay. Yeah, and then obviously, if you're within the page fault frequency, then the OS has various options for how to handle page replacement. Okay, so any questions about any of this? It's interesting because, again, if the global page fault frequency exceeds some upper limit, then all you can really do is say, I'm thrashing, or you can reduce the degree of multiprogramming. So the OS has very few things that it can really control in these situations. So global allocation policy, if the fault rate goes up too high, it needs to just stop processes. If you have a local allocation policy, then you can actually start using a single process's page fault frequency to figure out where to allocate frames. Okay. Interesting problem, but it just doesn't tend to be the way systems do it. Okay, let's see. Yeah, like I say here, it doesn't necessarily prevent thrashing, so you may still need to stop some processes. Yeah, like I say here, if the page fault frequency of many processes is high, then you would just have to start knocking processes out of the mix until the system starts behaving better. Okay, just to give you a quick description of how modern OSes that we use these days. This is basically a description of how Windows and Linux handle page allocation and page replacement. So basically they rely on a pretty sophisticated page eviction policy. What you'll notice, though, is that they all use page pools. And so they have a pretty sophisticated policy, but it's still allowed to make wrong choices because those choices can be undone by pulling pages back out of the page pool. Okay? So we let users run what they want to run. Okay? The user is the medium-term scheduler, so they decide if the system behavior is unacceptable. If you have a process that remains blocked, okay, this is the thing I was talking about before. If it's blocked, it can't use the CPU, it doesn't need its pages in memory, so the OS is going to start picking those things up. Hopefully it'll do it in an intelligent way. Okay? But ultimately the process is going to end up being completely removed from physical memory. Now this is very different from a local replacement or a local allocation policy. In a local policy, this might stay in memory, even though it's been blocked for a really long time. But if we have a global allocation policy, then this process would eventually be stripped of all of its frames. Okay. So Linux, basically demand paging. It doesn't allocate frames to a process until it gets a fault on the corresponding virtual page. All right. So that's pretty obvious. Heap and stack, basically doing exactly what you guys are implementing, demand zero paging, where I need a page and I need its contents to be zeroed out because I don't want to see what other processes had in their frame. Okay. So basically that's how that works. It uses something like clock. Notice it maintains an age for pages. And so that the neat thing about this is that the age is populated from the access bit. So the access bit is used to compute an age for the pages, but they decay. It's not necessarily the same as shifting it to the right like the aging policy does. Linux has a slightly different approach. But the ages still will decay over time so that if you have a big burst of accesses, then that value will look appealing and the pager will keep that page in memory. But it will eventually decay down to the point that it will get evicted. Okay, so that's a pretty important thing when you have anything using the access bit. So pages with a low age value will be reclaimed, but like I don't actually say it on here. There's a page pool. Linux has a dirty page pool and a clean page pool. And so if a page has a low age value and then suddenly is accessed by the process, there's a good chance that it'll still be in the pool, be reclaimed, and avoid a fault. Okay? So this is nice. This is basically what Linux does. Windows is a little bit more interesting. Windows actually expects processes to state their working set sizes. So Windows does more of a local allocation policy. Okay, you'll notice here that I say Windows calls it the working set. If you read Windows documentation, it'll say processes state their working set size. But the problem is, this isn't really the working set. The working set is defined by program behavior. This is more of the resident set. Okay, that's the way to think about this, is that you are stating your resident set. How many pages do I actually have resident in physical memory? Okay, so obviously, if the process has a stated resident set that's smaller than its working set, then we're going to be sad. We're going to have a lot of faults from that. Okay. So basically, processes are given a window, or they're allowed to specify a window. This is the smallest resident set I really want to work within. This is the largest resident set. And I have the defaults here. You can see 200 kilobytes for the smallest and 1.3 megabytes for the largest by default. But then a process can also state their working set sizes. Okay. So basically you can see how in Windows processes can say a lot more specific detail about what their resident sizes are. Okay. So how does this all tie together? Well, we have this situation that the OS may need more frames from time to time. Maybe you have one process that's faulting a lot, so we need to increase the number of frames that it has. So Windows has to get them from somewhere. And so what it does is a process called trimming, where it traverses all of the processes and basically says, what can you give up? Now, this is not something that the process actively participates in, but again, there's an aging policy that's applied to each process's working set or resident set to figure out what pages are good candidates for reclamation. Okay, so when trimming, Windows sets a goal. So it says, I'm seeing a lot of faults on this process. I estimate that its resident set or its working set is actually this large. It'll compute how many pages it wants, how many frames it wants to reclaim. Okay, so then what it does is it traverses all the processes in memory working sets and basically looks at their ages. Okay. And so, like I say here in Windows 7, each page has up to one of up to 8 age values. So maybe that means there's 3 bits that it's maintaining in a little working set type policy, like we described before. And basically, it tries to reclaim pages oldest or least recently used all the way up to most recently used. So it basically tries to mitigate the amount of faults that might occur by reclaiming stuff it thinks is most likely to not be in the working set anymore. Okay. The other thing that's kind of interesting about this is that Windows tries to be fair, so it will not stop once it hits its goal. So remember, it picks a goal for how many frames it wants to reclaim. Basically, it continues going through all processes because it wants to be fair to processes that came after it reached its, it wants to, how would you describe that fairness? It just tries to make sure that it reclaims from everyone equally and doesn't penalize some processes for, maybe having lower process ID or being in the collection earlier than some other process. So it goes through all the processes to reclaim those. Okay. Let's see. Final thing, they both use free page frame pools, okay, so that we can reverse poor decisions. Okay, and it's the whole thing that I described before, that if the page has not been modified, then it'll go in the clean pool. And when we have new page allocations that have to occur, we want to take them from the clean pool, not the dirty pool, because that will not incur the I/O overhead of eviction. But then we also have a dirty pool, and eventually those pages' contents are written out to disk, and then they can be migrated to the clean pool, and then ideally everything eventually becomes clean. Okay? So if you have a process faulting against a page that happens to still be in those pools, then it can just be moved right back. Okay? So any questions about any of this discussion? Yes?
Because like when you talk about the Windows procedure, like that's like very time intensive and computational intensive, like iterating through all the frames and all the processes.
Yeah.
And so it's the way that it basically justifies that by saying we're only doing this, like we're not doing this when we need one more frame. We're doing this when there's thrashing and we need to get like a large block. And like
I would hope that's its reasoning. Yeah. Because I mean, yeah, you definitely, like you said, you definitely don't want to do that amount of processing every time you need to allocate a new frame. Okay, and so yeah, I would imagine. Again, this is an area where, I mean, Windows is a closed source system, so it's difficult to know the actual details of it. But you can imagine that this might occur when the clean frame pool or the modified frame pools together went below a certain threshold. So you say, oh, okay, I'm starting to get low on available frames, so maybe I should go try to collect some. You can imagine it doing that. Like you said, if it started seeing thrashing on a significant number of processes, it could go ahead and run the trimming mechanism. So, but yeah, there's no reason to run it if everybody's happy. So it wouldn't make sense to do that because it would be too performance intensive. So you could come up with a couple of ways that it does it, but like I said, it's not entirely clear when it does it since it's a closed source system. All right, yeah, and that's the other thing that's nice about Linux is that it's a little bit more aggressive about moving pages into its free page pool using its modified clock algorithm. It can just keep running that and just periodically go through. Looks like you're not using this anymore. Throw it into the available page pools, and if a process says, "Wait a minute, I was using that," then it can just pull it right back out. And so that page pool actually starts to play a really significant role in making these systems work effectively and efficiently. I wish we had time to build one of these. It would be really cool to learn from it. But this is the kind of thing that would have to be relegated to like a CS81 or something like that. Any other questions? All right, well, thank you guys for coming. Let me see what I say here. Yeah, so next time, we'll probably start discussing file systems. I have a feeling that the hypervisor lecture will probably be the last lecture of the class, just because of how tired I am. So I'll probably throw that together over the next couple of weeks. There's so much material, too. I'd love to give 2 hypervisor lectures. But we'll see. We'll see what happens. So, all right, we'll see you all next time.